In this video, we will be discussing section 8.2, which begins on page 495 of your textbook. And in this section, we are going to be discussing applying exponent properties involving quotients. So that means we're going to be dividing today. Alright, so quotient of powers means I have first a division problem and then I have powers. So please do keep in mind that we discussed this in the last section. A is the base, and it must be the same in order to do this. So if I've got a quotient of powers, it's going to subtract the exponents as long as the base is not 0. So if I do one example, it would look like this. 9 to the 12th power, you could expand it and write it out 12 times. We're not going to do that. Alright, instead we're going to use these shortcuts. 12 minus 5 for the exponent, 9 to the 7th power. Well, you go ahead and pause the video and try the next 3 examples on your own. Alright, so as you can see, working from example to example, I'm consistently using that quotient of powers and subtracting the exponents since the bases are all the same. So in part C here, first I want to go ahead and combine my powers of 3 and 5 to get 8, and then I'll use the quotient of powers. So first I use the product of powers and then the quotient of powers. And here in part D, I needed to recognize that when I was multiplying 1 times r to the 8th, it's really just r to the 8th over r to the 5th, and then I can use my quotient of powers again. So your final answers should be 9 to the 7th, negative 2, because it was to the first power, I don't need to write that one exponent. Alright, 6 to the 6th, and then r cubed. Alright, moving forward, I've got the power of a quotient. So first, I have a power on the outside and then a quotient on the inside. And just like the power of a product, I take each piece of that quotient and I distribute my exponent. So looking at an example, use the power of a quotient property to simplify. So I'll go ahead and pause the video and you use that property. Alright, so looking at the solutions here, I have c to the 6th over d to the 6th, and then in part B, I've got negative 2 to the 4th over y to the 4th, and since I've got numbers and variables in the same problem, they want you to go ahead and simplify or actually multiply out that negative 2 to the 4th. Keep in mind I'm very careful and use parentheses there. And that will give me a positive 16 over y to the 4th. So moving on, I've got a couple more examples. So why don't you go ahead, make sure that you are distributing that exponent to every single piece of that quotient. So go ahead, pause the video and attempt it for yourself. Alright, so I expect that some of you might have had some issues with the second one because there were quite a few number of steps here. So when you distribute that exponent to every single part of that quotient and the products within the quotient, for part A, you should have multiplied out that 3 cubed and that 5 cubed and gotten 27 to the 12th power over 125 b to the 3rd power. But then in part B here, there is a couple more steps we've got to go through. So first, I do distribute that 7th power and eventually end up with x to the 21st power, or x to the 21st power over y to the 7th. And then when I combine and actually multiply across here, I get x to the 21st power over 3x to the 8th, y to the 7th. Typically we put the variables in alphabetical order. And then since I did have a couple of x's in a quotient, I went ahead and used my quotient of powers there and subtracted in order to get x to the 13th power divided by 3 y to the 7th. Alright, and we've got just 2 more examples for you. So, in example 4, they want us to construct a fractal tree that begins with a V shape with each side 1 unit long. Alright, and at the end of that, add a V shape with half a unit long. So I'm just going to follow it line by line. So here is my V shape, here is my V shape, and I'm going to say that that is 1 unit long. I'll actually do it sideways. Alright, that is 1 unit long, and at the end of each V, so at the end of each V, I'm going to construct one that is half that length. Another V. Alright, and then it says to keep going as long as it is half of that length, Alright, and I'll try it one more time until I get little itty bitty. So this is a fractal, it is a pattern, and we use exponents to create these. Alright, you can see them in nature a lot with snowflakes. Alright, and flowers and trees and lots of things in nature. So, make a table showing the number of new branches at each step, step 1 through step 3. So first, let's go ahead and create a little table here. We'll put step number, and branches. Alright, and it does specifically say new branches. So at step 1, you have 2 branches. At step 2, this is your red step. Step 2, you have 4 branches. Step 3, you have, this is kind of your multicolored one, you have got 2, 4, 6, 8 branches. Right, and at step 4, step 4 is the little gray one, you have got 16 little branches. So I didn't read the directions fully, so it does say to write it as a power of 2. So I'm going to rewrite this. Step 1, 2, 3, 4, and then write it as a power of 2. That's 2 to the first power, 2 squared, 2 cubed, and 2 to the 4th power. Alright, how many times? So when we say times, it is multiplying. As great is the new number of branches in step 6 as the number of new branches at step 2. So it would probably help to figure out how many branches there are going to be. So if I look at my pattern, that's going to be 2 to the 5th, 2 to the 6th. So here's step 6. And they say step 2. Okay, so that is 2 to the 6th power. Equals something, I don't know, a number, how many times, we'll just put t for times, as the number in step 2, so that's 2 squared. So in order to solve for t, you need to divide, so that's 2 to the 6th divided by 2 squared, or 2 to the 6th minus 2, or 2 to the 4th power. So it is actually 16 times as great. So using similar logic, won't we go ahead and attempt example 5? I'll read it. The order of magnitude of the luminosity of the Milky Way galaxy is 10 to the 36th power watts. The order of the magnitude of the luminosity of a gamma ray burster is 10 to the 45th watts. How many times as luminous is the gamma ray burster as the Milky Way? So go ahead, pause the video, and see if you can figure it out. Alright, and if you had set it up just like the last problem, you should have gotten 10 to the 9th times as great. Alright, if you have any questions, please let me know via email.